Jai Hind. I am Ms. Lipika Goel, Assistant Professor, Department of Computer Science and Engineering from Ajay Kumar Garg Engineering College, Ghaziabad. Today, I am going to cover the topic on disk scheduling from operating system. Let us start with disk scheduling. This is the picture of the moving head disk mechanism. Here we can see this is known as the ARM assembly. These are the different disks, and in across the spindle, this is the center axis is known as the spindle, along which the rotation of the disk takes place. This is the platter. Then we have the cylinders, and so this complete section is called the cylinder. These are the tracks, and in the tracks we have the sectors. So these are the different sectors. Then we have a read-write head, which is the read-write head points to a particular sector for reading and writing, and then this is the arm. So this is the general head disk mechanism. What is the definition of disk scheduling? Disk scheduling is done by the operating system to schedule the input-output request that is arriving for the disk. So we have the different input-output requests that is arriving for the disk. So there has to be some scheduling mechanism that has to be implemented by the operating system to schedule these input-output requests. This is known as disk scheduling. So disk scheduling is therefore also known as input-output scheduling, because it is scheduling the input-output request that is arriving for the disk. Disk scheduling is important. Why? Because there are multiple input-output requests that arrive for the different processes, and only one request has to be served at a time by the disk controller. So there need to be so the other requests need to wait in the waiting queue, and it need to be scheduled. So therefore, there is a requirement for a disk scheduling algorithm. Two or more requests may be far from each other, so can result in a greatest disk arm movement. And hard drives are one of the slowest part of the computer system, and thus they need to be accessed in a very efficient manner. There are many disk scheduling algorithms. Let us quickly have a look at some of the important terms that we use in disk scheduling. First is the seek time. Seek time is the time that is taken to locate the disk arm to a specified track where the data is to be read or written. So the disk scheduling algorithm that gives the minimum average seek time is better. Means if I look at the diagram again, this disk arm, the time taken by the disk arm to move to that specific track from where the data has to be read, this is known as the seek time. Next is the rotational latency. Rotational latency is the time that is taken by the desired sector of the disk to rotate into the position so that it can access the read-write heads. So the disk scheduling algorithm that gives some minimum rotational latency is better. So if I go to the diagram, here is the read-write head. The time that is taken now in this track, say this sector, the data has to be read. So the time that is taken to rotate and reach to this read-write head so that the data can be read, which is in this sector, this is known as rotational latency. So it should also be as minimum or as low as possible. The third term is the transfer time. Transfer time is the time that is required to transfer the data. Now again, it depends on the rotating speed of the disk and number of bytes to be transferred. And then this is the important disk access time. This is the sum of the seek time, the rotational time, and the transfer time. So the sum of all these three is collectively known as the disk access time. Then we have the disk response time. The response time is the average of the time that is spent by a request waiting to perform its input-output operation. Means suppose an input-output request is there, how much time it has to wait for the scheduler to be assigned and that request to execute. So average response time of all the requests, it should be as low as possible. Now there are disk scheduling algorithms there are several disk scheduling algorithms which exist to service the multiple disk input output request which we get. We are going to take this example. We illustrate them with the request queue from 0 to 99. Let's say the head pointer is at 53. So we are going to consider the first disk scheduling algorithm, which is FCFS, first come first serve disk scheduling algorithm. Now it is given in the question that this is the queue: 98, 183, 37, 122, 14, 124, 65 and 67. So head starts at 53, and in the question it's already given the request queue is from 0 to 199. So we are drawing one number line, say from 0 to 199. Then we have a request at 14, 37, 53, 65, 67, 98, 122, 124, 183. Suppose we have just marked these, and we know that the head is starting at 53. Head is starting at 53. So current position is at 53. This is FCFS scheduling. So the request that came first is 98. So our head will go to 98. The next request that gets in is 183. So then from 98 it will go to 183. Next is 37. So from 183 again it moves to 37. From 37 to 122. From 122 to 14. From 14 to 124. And from 124 to 65 and then to 67. So this is the head movement depending on the request, input output request, which is in the queue. So if you have to calculate the total head movement, what will be the total head movement? It is, first is 98 minus 53 plus, next movement was from 98 to 183. So it will be 183 minus 98 plus, next movement was from 183 to 14. Sorry, 183 to 37. So it will be 183 minus 37. Next will be again from 37 to 122. So it will be 122 minus 37. Next will be from 122 to 14. So 122 minus 14. Then the next will be from 14 to 124. So it will be plus 124 minus 14. Then the next was from 124 to 65. 124 minus 65 plus the next was from 65 to 67. So 67 minus 65. And the sum of all these will be the total head movement. So what is the total head movement? This distance followed by all these, sum of all these distances that is covered. This is FCFS disk scheduling. So here we are calculating the total head movement. So the minimum total head movement is the optimal solution. Next is shortest seek time first. In the shortest seek time first, we select the request with the minimum seek time for the current head position. We are going to move our head, current head, to that particular request which has the minimum seek time. SSTF scheduling is a form of SJF scheduling and may cause starvation of some request. So let us consider next same with SSTF. Again we have numbers from 0 to 199. Current head position, head starts at 53. So the current head position is at 53. Now in FCFS we were simply following the queue. Here we are seeing the seek time. What is the minimum time required? So from 53, if it goes to 65, that is the least distance that it will cover. So it first goes to 65, then to 67. Now the nearest request from 67 is, so 65 is done, 67 is done. From 67, the nearest distance that it has to cover is 37. So it goes to 37. Then from 37, the closest next request is at 14. So it will go to 14. It is seeing the shortest seek time. From 14, the next nearest one is none other than 98. From 98, then it goes to the next nearest request, that is at 122. From 122 to 124, and from 124 finally to 183. So this is the shortest seek time first. It is not serving the request depending on the requests which are there in the ready queue, but it is first calculating on servicing which request I have to cover the shortest distance. So it saw when it is at 53, it saw if I go to 98, I had to cover more distance. So instead of going to 98, let us look at that particular request that will require to cover the least distance and that will be serviced. So 65 was the nearest one. So it went to 65, then to 67 and so on. So similarly, in the similar way as I calculated in my last example, we are going to calculate the total head movement. The total head movement. So on calculating the total head movement, again from first, it travelled from 53 to 65. So it will be 65 minus 53 plus 67 minus 65 plus 67 minus 37 plus 37 minus 14 plus from 14 it went directly to 98. So it will be 98 minus 14. Then from 98 it went to 122. So 122 minus 98. From 122 it went to 124. So 124 minus 122. And similarly at last from 124 it went to 183. So it will be 183 minus 124. And sum of all these will give you the total head movement. Sum of all these will give us the total head movement. So these are the distances actually that we are adding it up to calculate the total head movement. Next algorithm is the scan. In the scan, the disk arm starts at one end of the disk and moves towards the other end, servicing request until it gets to the other end of the disk, where the head movement is reversed and servicing continues. So scan is also sometimes known as an elevator algorithm. Why elevator? Because when it starts from the current head position, it moves on to one direction, servicing all the request which comes until it reaches the end of the disk. After the end of the disk, it reverses its direction and servicing the request continues. So it is same the movement is as in the case of a lift. Let us take it as an example. Again the same scenario from 0 to 199, current head position is at 53. Now suppose we are moving it in this direction, say on my left. We can move it in either of the directions. So from 53 it goes to 37, from 37 to 14, and then it will go until it reaches the end, because it sees whether there are more requests in this or not. After that it reverses its direction and it services the request if they are pending. So at its way, then it got 65, then it got 67, then to 98, then to 122, then to 124, and finally to 183. So you see the movement here is in the form of lift. It is going into one direction till it reaches the end. Then it reverses its direction and keeps on servicing the request on its way. So therefore it is known as an elevator algorithm. So this is how the scan works. And the total head movement will be the sum of all these distances as we have calculated in our previous example. Next is the C-scan. So it will provide a more uniform waiting time than the scan. Here the head moves from one end of the disk to the other, servicing the request as it goes. When it reaches the other end, however, it immediately returns to the beginning of the disk without servicing any request on its return trip. Now if you see here, when it is reversing its direction, it is servicing the request on its return trip. It is not that it directly went to that end. But in the C-scan, which is the circular scan, here it starts servicing its request in one direction, reaches to the end, and in its return trip, it does not service any request but goes to the end of the disk and then it services the remaining request. Let us understand this with the help of an example. Again, we have numbers from 0 to 199. This is the Q. The current head position is at 53. Again, we can move in any of the directions. Suppose here we are moving towards the right. So it goes from 53 to 65, from 65 to 67, then to 98, then to 122, 124, 183, and it goes to other end of the disk as we were going for scan. So it reaches till 199. What was happening in scan? On its return trip, it services the remaining request. But here in C-scan, it will directly come to the initial point 0. And then it will start servicing the request 14 and 37. So here it is moving it in a circular fashion. So this is C-scan, and it will give a more uniform waiting time as compared to scan. And when we can always calculate the total head movement, that will be the sum of these distances as we have been calculating in the previous examples. Coming on to the next algorithm, which is LoOK. LoOK is similar to the scan disk scheduling algorithm, except for the difference that the disk arm, in spite of going to the extreme ends, it goes only up to the last request, and then it reverses its direction and serves. So it prevents that extra delay. Here you can see, even in the C-scan, there was an extra delay of this. There was no request from 14 to 0, but it reaches to the end. Similarly, in the C-scan, we can see there is an extra delay because it goes till end here, and then again it reverses its direction and reaches to the other end. So this is the extra delay. This extra delay is overcome in the case of LoOK. See, you can see this example. Suppose we have disk from 0 to 199, and here say the current head position is at 50, and we are moving it in any one particular direction. Say we are from 50, we went to 82, then to 142, then to maybe 170, then the last request is till 190. So here we are not going to 199 as we are going for scan. We'll stop here at 190. And then we are going to return, reverse, and if any request is in between, say it is 43 is there, then 24 is there, and then 16 is there. So we are going to service the request on a return trip. So the only difference between scan and LoOK is that scan is going to the end of the disk, but LoOK is going only up to the last request. So that extra delay is saved. And then we can calculate the total head movement, or the seek time, that is the sum of all these distances, right? So we can calculate it directly also, that is 190 minus 50 and 190 minus 16. This is the total head movement, or we can say the total seek time. Coming on to next, CLook. Again, CLook is just a version of C-scan. As we have scan and C-scan, we have LoOK and CLook. LoOK was just a version of scan, and C-scan and CLook are the versions. So version of CLook is C-scan. In C-scan, same way, it services request, and then it reverses, it goes as far as the last request in each direction, then reverses the direction immediately without first going all the way to the end of the disk. So like in this example, suppose the head is at 53. We are going to one particular direction from 53 to 65, 267, 98, 122, 124, 183. 183 is the last request. We are stopping here. We are not going to 199 as a scene of C-scan, and we are returning back and getting to the first request 14. If you remember, in the C-scan we were going to that up to 0. So here we stopped at the first request 14. And then servicing the remaining request. So here the only difference is we are just avoiding that extra delay to move to the end of the disk. We are only moving up to the last request, reversing its direction and coming up to the first request, and then servicing the remaining one. So this is again circular LoOK. For the total head movement, we can calculate in the similar way. Here if you look, the last request is at 183. So it will be 183 minus 15, then the total seek time or the total head movement, 183 minus the head movement was 53 plus this distance, this is again 183 minus 14 plus this distance, that is 37 minus 14. So the sum of all these three is the total head movement, or you can calculate it in the individual way, the addition of all these distances will give me the total head movement or the total seek time. So these are the different disk scheduling algorithm. That is, we have FCFS, scan, C-scan, look and CLook, and a shortest seek time first. Selecting and scheduling, disk scheduling algorithm, SSTF is the most common and has a natural appeal. Scan and C-scan, they perform better for the systems that place a very heavy load on the disk. Performance depends on the number of types of request. Request for disk service can be influenced by the file allocation method. The disk algorithm should be written as a separate module of the operating system, allowing it to be replaced with a different algorithm if necessary. So either SSTF or look is a reasonable choice for the default algorithm. So usually in default, we either go for look algorithms or shortest seek time first. Thank you.